Good morning or good night or whatever it is. How many here have seen a comet in real life? Oh, a couple. Me too. I saw a Hale Bopp actually when it was here in 1997. Uh, Here's another example of a comet. This is comet Ikea Zhang, also known as, 153P. What is a comet really? Well, you can see it has sort of two parts here. There's a more or less spherical region here, which we call the coma, and there's this long tail coming out behind the coma. So what's the coma? Well, inside the coma, there's a tiny nucleus of the comet, which is basically a piece of ice. So we usually say a comet is like a snowball or a dirty snowball. So it's mainly ice and also some dust and maybe some carbon and other organic material. Now, when this snowball gets close to the sun, of course, the solar radiation melts part of the snow, and that comes out as gas and dust into space. So this forms a relatively weak but still existing atmosphere around the nucleus. Now, an atmosphere, when the sun shines on the atmosphere, becomes partly ionized. Same thing as happens at the Earth's atmosphere at the upper level, creating something called an ionosphere, which is a plasma. How many people here know what a plasma is? I see a couple of my students here, you should know. So a plasma is a partially ionized gas. So it's a gas where the atoms have been split up into a positive ion and a negative electron. So it can actually conduct current just as a metal. So that's the coma. It's an atmosphere and a partly ionized ionosphere. And then we have this long tail, which is actually produced by both the solar radiation, the sunlight, which actually pushes on the particles, mostly the dust in the coma, and creates this long tail, and also the solar wind, actually, which is again a plasma which is continuously sent out from the sun, and actually also pushes away part of the coma in this long tail. There's also an extra complication. You can maybe see there's some structure in this tail, and that's due to the magnetic field which exists in the solar wind. This magnetic field actually gets hung up like long spaghetti straws around the coma here and creates structure in this long tail. So I'm going to talk a little bit about another comet, Comet 67P, also known as, and I have to take a breath, Churymov-Gerasimenko. Takes a bit of practice. So here we see a really nice close-up picture of the inner part of the comet, the actual dirty snowball here. This is around 4 kilometers in both these directions. And you can see when the part of the comet is sunlit, you can really see that there's a really massive outflow of water vapor and dust. And you can see sometimes when the sun hits particular regions on the comet nucleus, you can get these really clear jets blowing out into space. A bit further out, this becomes more spherically symmetric and creates a more spherical atmosphere. Also, this comet nucleus rotates with a period of around 12 hours, so that also helps to make things more symmetric. We have studied this comet quite closely by the Rosetta spacecraft, which was built and launched by the European Space Agency. And this is around 2 times 2 times 3 meters, this body here, also with the addition of the solar panels. You can see there's a large number of scientific instruments on this spacecraft. And I personally have been involved mostly in the instrument called LAP, Langmuir probe, which are these two booms here with a small spherical metal spherical spheres, at the end of the booms. And I'll try to explain a little bit later what we can do with these. There's also this kind of little extra baby spacecraft, which I'm not going to talk about today, but it was called Philae and actually landed on the comet surface, which was quite exciting. Now, the journey of Rosetta towards the spacecraft was quite a long one. It was actually launched in 2004, and then it made some very complicated maneuvers and actually went by a couple of the planets, both Venus and Mars and Earth. Not Venus, just Mars and Earth, in a kind of a cosmical pinball game. And if you do this intelligently, you can actually save a lot of fuel and get to the comet in the most economical way. So this took around 10 years until we reached the comet. And there was a particularly nervous part when the spacecraft was shut down to save power for a couple of years. But then it woke up nicely, as it should, in January 2014. And then it reached the comet in August 2014. Then it followed the comet for almost 2 years, during which we made very nice measurements at a distance from typically between 10 and a couple of 100 kilometers away from the nucleus. So, like I said, I was involved in the LAP instrument, and with the LAP instrument we wanted to measure the electric field. And now I'm going to make a sort of a very popular description here for if there's someone who's not into space physics or physics at all. I want to say a little bit about what is an electric field. Well, in physics we define an electric field as an electric voltage. For example, if you take this power socket, which you can see in the wall, there's a voltage, electric voltage between these two poles. It's 230 volts in our power outlets. If you take that voltage and divide it by the length between these two poles, you get the voltage divided by distance, and that's the electric field. So for this, I actually took a ruler earlier tonight and measure how far this is, and it's 2 centimeters. So if I calculate the electric field close to this power socket, it would be 230 volts divided by 2 centimeters, or 0.02 meters. That gives me, I have to check my notes, that gives me 11,500 volts per meter. Help me to remember that, right? So that's quite a big electric field. Now, we do exactly the same thing with our spacecraft here. If you remember these two probes, these two booms with the probes at the end. Actually, what we do is we measure the voltage at one probe and the voltage at the other probe. We take the difference, that gives us the voltage between the probes, and we divide by the length L. And from our measurements, it's typically we have voltages of around 1/4 of a volt, 0.25 volt or so, divided by the 5 meters between these two probes. That gives us an electric field of around, let's see, I got something like 50 millivolts per meter, compared to what was the electric field at the, thank you. So that's around a 1/1,000,000th of the electric field we have in the power socket. So it's in space, electric fields are usually very small. On the other hand, they extend for very large regions, over very large regions. So actually the voltage might be quite significant. So, what do we see when we make these measurements then? So here's an example. So these are some measurements from when we were close to the relatively close to the nucleus, around 100 kilometers away. And here, from top to bottom, we see the voltage of one of the individual probes, which actually, it turns out, is a very nice indication of the density of the plasma around the comet. So you can see you have this high density over here, and then there's a sudden drop in the density. There's some structure with a high density with a sharp boundary, and then you have a low density. That's also there's also an instrument which measures the magnetic field, and you can actually see that this is anti-correlated with the density. So when there's a drop in the density, there's an increase in the magnetic field. To me, by the way, this is a parenthesis, this indicates there's maybe some kind of pressure balance, because a high density means a high pressure, low density means low pressure, but there's also there can also be a magnetic pressure. So you see, when there's a drop in the plasma pressure, there's an increase in the magnetic pressure. There seems to be some kind of pressure balance. Now, what happens at this very sharp drop in the plasma density is that that's where we see very large signals in the electric field, which is the difference then in the voltage between the two probes at the booms divided by the length. And like I said, it was like typically 50 millivolts per meter, which we see here. So you see these large variations in the electric field at this boundary here. If I blow that up, it looks like this. So these look like very nice wave signatures like this in the electric field. Now, waves in the electric field, that's typically, this is an example of some kind of plasma wave, as we call it. In vacuum, there's only one kind of electromagnetic wave. It's the ordinary light or radar waves or microwaves. They have a certain relation between the electric and the magnetic field in the waves. In a plasma, we can have much more complicated waves. We can have several different types of waves. Well, many different types of waves. When I had a look at these waves and analyzed them more closely, it turned out that these are probably, I think, something called lower hybrid waves, which are a certain type of waves that typically exist when we have large changes in the plasma density and also typically large changes in the magnetic field. And I could calculate this from the magnetic field measurements. I could actually calculate the expected frequency of these waves, and it turned out to be exactly what I expected. So I think these nice waves are an example of the lower hybrid waves. Now, this to me is very exciting, lower hybrid waves, because if you go and listen to one of the fusion talks later on, I think tomorrow, they actually use lower hybrid waves to try to heat up the plasma inside fusion reactors, to accelerate and heat the plasmas to try to start the fusion reactions going on. Of course, we don't have any fusion reactions close to the Comet, but we can expect that these lower hybrid waves actually heat the plasma around the comet. And that, I think, is probably the main interesting point of these waves. They will probably try to modify the region inside in the inner coma, the region around the comet, and change the environment around the comet. So understanding these waves are a step towards understanding the space environment around a comet. And we can actually make some quite detailed predictions about how these lower hybrid waves will heat the plasma. For example, we know that lower hybrid waves, they like to interact with both electrons and ions. And the way they accelerate electrons is that if the velocity of the wave happens to be the same as the velocity of the electron, the electron will feel a constant electric field all the time, accelerating the electron as the wave travels with it. Now it turns out that the wave will try to accelerate electrons along the direction of a magnetic field. And like I said, there's a magnetic field in the solar wind. You can actually see how it makes this spaghetti-like structure here in the tail. So we can predict, or we will predict, that these waves will accelerate electrons along the magnetic fields. But it will, on the other hand, try to also accelerate ions, but perpendicular to the magnetic field. So we have classical scientific methodology here. We make an observation, from that we make a prediction, which we can now test. And the nice thing is that there are instruments on the Rosetta spacecraft that measure the energies of both electrons and ions, in both along the magnetic field and perpendicular to the magnetic field. So what I want to do now, the next 6 months or so, is to go back to my colleagues, have a look at the data for the ions and for the electrons, and try to see if they are accelerated as we predict by these lower hybrid waves. So that's what I'm going to spend my next 6 months doing work on. And with that, I say thank you.